All right, good morning, everybody. I'm Lieutenant Timothy Mueller, and I'm going to be the instructor on Lesson 4, where we're going to be talking about the Transverse Metacenter here in the curriculum for Damage Control Assistant and Senior Enlisted School. In the previous lessons, we talked about moment couples, moments, and then we started going to the writing arm and writing moments. Now let's bring that all back into a diagram and introduce what's called the stability triangle, as well as the Transverse Metacenter, which is the topic of this lesson. So you've seen this diagram. I've added a few more details to it. This is a ship underway steaming and just rolls over to the side for whatever reason. We have the center line of the ship going right through here. We have the center of gravity, the initial center of buoyancy. When it's rolled over, it swings through this arc over here. If you take this line of force acting directly through B, draw it straight up, and you draw this point where it meets the center line, as long as that ship is inclined through a small range of angles, such as, like I said before, 0 to 7 or 0 to 10, depending on the hull size or hull shape, this point where the force of buoyancy meets the center line is called the metacenter. The metacenter, as long as you're within that small range of angles, is always going to remain in the same place. We have this distance from B to M is called the metacentric radius, because this center of buoyancy swings through this arc where the center is the metacenter. The center of gravity is going to remain the same on that vessel as long as no cargo shifts or no liquid load changes, which, as we'll see in later chapters, is actually the case. That center of gravity has a virtual rise to it with liquid loading. But for now, we're just going to assume that G stays in the same spot. We've already learned about this point Z, which is the perpendicular distance from G to this line. So we know that GZ is our writing arm. Now let's look at this triangle here. Let's blow it up and kind of see some cause and effect relationships. So we've blown it up here. We have K being the keel. Here's our center line of the ship. Here's the vertical active buoyancy through B1. This is that center of buoyancy that's over where B0, B0 is right along the center line. Then we have center of gravity naught, which is what we'll have in this diagram, and Z naught, giving us GZ naught, which is the initial writing arm. All right, so let's assume that the center of gravity always stays along the center line of the ship. If we raise the center of gravity so it follows vertically along that center line, we're going to go from G0 to G1. Okay, now let's assume we're at the same angle, so everything's staying in this triangle. If we raise that center of gravity, we have to take the perpendicular distance from that new point of gravity all the way over to the force of buoyancy, or sorry, the line of force of buoyancy. That's going to give us a new Z1, which gives us a new writing arm in total of GZ1. Okay. If you look at this, this is our initial GZ naught, and this is our GZ1. GZ1 is notably smaller, notably shorter than our initial GZ. And that makes sense. If something becomes more top-heavy, as we make that center of gravity go up higher and higher and higher, we kind of intuitively think, okay, it's less stable. Here, we're actually starting to see it. We have a smaller writing arm, which means that if the displacement stays the same, we have less of a writing moment that's going to want to kick us back into our equilibrium position, which is straight on an even keel. If we do something like add liquid ballast down low, then we're going to have a center of gravity drifting down along the center line of the ship. Now we're going to talk about G2. G2, right here, has a perpendicular distance to the line of buoyancy and meets at this point Z2. If we have GZ2, we take this line, it's noticeably longer now than GZ naught. So if we add weight low or remove weight high, basically do anything that drops that center of gravity, we're going to get a longer righting arm. If the displacement stays the same, which means if we're not adding weight or taking away weight, it means we're shifting weight down, then that means that we have a larger righting moment that's going to be kicking us back into that equilibrium even keel position. So how do we find this GZ? Okay, there is a way that we do it. We find it on statical curves of stability, which we'll get to later. However, if you look at this triangle and remember back to basic trigonometry, you can see that GZ, the opposite side to the angle theta, which is what we're inclined over to, GZ equals GM, which is the distance from the center of gravity that you have up to the metacenter, times the sine of theta. Now there are several different ways to calculate, Km and Kg, and then you can find your GM that way. We'll get into that in chapter 3, because there are several different ways to estimate and get good approximations of it. However, just realize, if you know your GM, say it's 3.5 feet, and then the next day you have a GM of 3.4 feet, then you're saying, okay, that means that my center of gravity has just drifted up 0.1 feet. Because now the distance from G to M, where it was 3.5 feet yesterday, is now 3.4 feet, which means that my righting arm, my righting moment, and everything that goes with it is now a little bit less. Is that a cause for concern? It might be. You might be within your operating criteria for the ship in whatever situation you're in. You might not be. That's for you and the captain to decide. However, just always remember, as G moves, that righting arm moves as well. A couple quick notes on the stability triangle here and everything I've talked about. 1, small angles, the metacenter stays still. Small angles being from 0 to 7 degrees, or depending on the hull shape, could be 0 to 10 degrees. But that metacenter is always going to stay in the same spot, as long as you're in those small ranges. As your kg gets larger, so the distance from the keel to the center of gravity, so if we go up here, our gm gets smaller, the distance from G to M gets smaller, and if we go here, if that sine theta is the same, gm was smaller, our gz gets smaller. Inversely, if we take kg to get smaller, so the distance from the keel to the center of gravity gets smaller, meaning we're going from here to here, our gm gets bigger. So the distance from G to M goes from here to here. With that increase in gm, now we increase our gz, our righting arm, and if our displacement stays the same, then our righting moment increases. Here's a quick little thing for you to ponder. Is it always good for G to be as low as you can possibly make it? Think about the different kind of ships that are out there. Some are very small ships, some are extremely large ships, like cruise ships. If you have a very tall ship and it's whipping all around, if you have a very, very strong righting moment, is that going to cause any undue stresses on the very top of the superstructure? Is it going to be very comfortable for people to ride in? Think about it real quick. So in this video, we talked about the transverse metacenter. We kind of introduced the concept of it, as well as took a look at the stability triangle. We reinforced what we learned about the righting arm, righting moment, and we saw how the righting arm changes as the center of gravity changes. As center of gravity goes up, we have less of a righting arm. Center of gravity comes down, we have a bigger righting arm. In the next lesson, we're going to be talking about positive stability, negative stability, neutral stability, and different conditions that we have with G. As you've probably already thought, G, there's always a force acting down, and B is always acting up. So we always have this moment trying to go this way. What if G goes higher than M? Think about that for a second, and then join me on the next video. But until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.